And here are answers for the Unit 6 review problem set. This chunk of the video is just the paper 1 questions, numbers 1 through 11. First up, question number 1. What is the equilibrium constant expression for the following equation? Remember that we're looking for Kc. This is looking for Kc, and that is the ratio of the concentrations of the products over the concentrations of the reactants. So find your products first. We're going to put that on the top. We're going to put the brackets around it to show concentration, and my coefficients become exponents. On the bottom, I need my reactants. We're going to put NO2 on the bottom. That 2 becomes an exponent, F2 also on the bottom. And we do not add, even though we have an adding sign here, it's a multiplication in our Kc, which means that our answer is going to be choice D. Question number 2, what is the pH of a 0.001 moles per cubic decimeter sodium hydroxide solution? It might be tempting to say that pH is the negative log of the concentration, and so our pH is 3, and you're like, haha, it's B. But we know that that's wrong, because we see that this is a hydroxide, not an acid. This is a hydroxide, and so I've actually found here, this 3 is not the pH, it's the POH. We found the POH because this is a hydroxide, not a hydrogen ion concentration. So I also know that because pH and POH add up to 14, if I substitute that 3 in for the POH and solve for pH, we're going to get a much better answer, 11. Question number 3, what is the major reason that the pH of unpolluted rain is less than 7? You might be tempted to pick one of our nitrogen oxides, sulfur oxides, but these lead to polluted acid deposition, acid rain, acid snow, acid hail. So these guys are not the answer since I'm looking for unpolluted rain. Unpolluted rain is slightly acidic due to CO2. Question number 4. This one's an interesting question. So they give us the reaction. We have this data table showing us different values of the equilibrium constant at different temperatures. Let's analyze this data super quick. Notice that the temperature is going up and the value of the Kc is also going up. Remember that Kc is the products over the reactants. As we get hotter, I'm having an increased Kc, which means that my products are getting bigger and my reactants are getting smaller. The hotter we get, the more product, the less reactant, which is why the value of that Kc, that ratio, is getting greater. My numerator is greater than my denominator. So that means I'm making more and more product. More and more product means that the equilibrium is shifting to the right, and that forward reaction is favored. Question number 5 is asking us to find the Bronsted-Lowry acids in this reaction. Remember that Bronsted-Lowry acids are proton donors. So I'm looking for the species that have 1 proton more than the thing that looks like it. So I'm noticing that these two guys look alike. This one has H2, this is only H1. This guy has 1 proton more, it's my acid. If I compare the other two things that look almost the same, I notice that there's 2 H's, there's only 1 H. This guy has 1 proton more, it's also my acid. This would be the conjugate base, and then also this would be the conjugate base. Here's a base, here's a base. But my question is asking for my 2 acids. So I'm looking for the answer choice that has H2PO4- and H2O, which is going to be choice D. Question number 6, order of increasing pH for the following solutions at the same concentration. So this is important, same concentration. Remember that pH of 7 is neutral. The further away we get from 7 under 7, the stronger the acid. And the further away we get from 7 over 7, the stronger the base. Or it could also be more concentrated, less concentrated, but it tells us that we've got the same concentration. So we really just care about strength of our acids, strength of our bases. So increasing pH, we're looking for the thing that has the lowest pH first, and that's going to be our strongest acid. And then I'm going to look for a weaker acid, and then we have that 7. And then I want a weaker base, and then the strongest of our bases. And that's going to give us choice C. HCl is our strong acid, ethanoic acid is weak, ammonia is a weak base, and then sodium hydroxide is a strong base. And again, we can answer this question because it tells us same concentrations. Question number 7. 10 cubic centimeters of an aqueous solution of sodium hydroxide pH 10 is mixed with 990 cubic centimeters of distilled water. What is the pH of the resulting solution? Two options. First, I'm going to show you the longer way, the mathier way, and then we'll talk about the more conceptual way. So first up, since I am diluting my sodium hydroxide solution, I can use M1V1 equals M2V2, our dilution formula. How we can use this, I'm going to take my V1 here. I'm going to use pH to find my M1. How are we going to do that? Well, first up, I've got a hydroxide. So be careful if you're looking at a hydroxide and you want to go from pH to concentration, we first need to go to pOH. So if the pH is 10, remember that pH plus pOH add up to 14. So the pH is 10, the pOH is 4. We get this by finding the negative common log of the hydroxide concentration. Negative common log is what is the negative exponent on a 10 to find that concentration. So if 4 is my negative exponent on the 10, I'm just going to put that 4 back as a negative exponent on a 10. So 10 to the minus 4, or 0.0001, is my concentration in moles per cubic decimeter. Here is M1. What about V2? So V2 is not, my friends, it's not exactly 990, because we're mixing with this original volume and this new added water. So V2 is actually going to be those 10 that we started with, the 990 that we just added. And so our new final volume is actually going to be 1,000 cubic centimeters. I'm going to plug that in for V2. Solve for M2. Good. M1. 0.0001 moles per cubic decimeter, volume 1, 10 cubic centimeters. Set that equal to M2 times V2, 1,000 cubic centimeters. Divide both sides by 1,000. And we're going to get M2 is equal to 10 to the minus, let's see, this 10 is going to make that guy look that way, but then I've got 1, 2, 3 zeros on the bottom, so 1, 2, 3 that way. I've got 1, 2, 3, 4, 5 zeros, 10 to the minus 6 moles per cubic decimeter is going to be my new concentration. So the pOH is going to be the negative log of 10 to the minus 6, which is going to be that 6, which means that the pH, my friends, is equal to 8. Answer is 8. Good. So here is the faster, more conceptual option for solving this problem. So if I have 10 cubic centimeters with a pH of 10, and thinking about common log base 10, we're all about powers of 10. So if I were to dilute my 10 cubic centimeters to 100, this is now 1/10 the concentration of this, which means that I'm going to drop my 10 to the minus 10 down to 10 to the minus 9, because it's 1/10 of it. And then if I dilute by a factor of another 10, go from 100 to 1,000, then again, my concentration is moving by another decimal place, which is another piece of the common log, which takes us to a pH of 8. And there's our answer. So I think this way is more concrete and obvious, but way slower. This one's a little bit more thinky, big brain, but way faster. Both are good, both are right, both got us to the right answer. So whichever way makes more sense to you is the right method for you to solve that problem. Question number 8. Which statement is incorrect for our 0.10 moles per cubic decimeter methanoic acid solution? Remember that methanoic acid is an example of a weak acid, which means that it is only going to partially dissociate, only partially ionized. So choice D is correct about this methanoic acid solution. It is not incorrect. So D is not our answer because it's right. Good. So when methanoic acid does dissociate, it's going to dissociate into this guy, and this guy will have the HCOO minus ion and the H plus ion. These guys will be equal to each other. They'll be very, very small concentrations, but they will be equal to each other. So this one is a correct statement, which means that it's not our answer. Do we feel like that hydrogen ion concentration is going to be much, much less than the concentration of the acid itself? Yes, because it's only partially dissociating, and so we're going to have a very, very small amount of H plus, not equal to that guy. This one is correct, which means it's not incorrect. It's not our answer choice. Can the pH be equal to 1? If I had a 0.10 moles per cubic decimeter strong acid that completely dissociated, then I could take the negative log of that 0.10 and find a pH of 1. That would be true for a strong acid, but since this guy is not a strong acid, the pH will not be equal to 1, which means that this is incorrect, which means it is our correct answer. Good. Question number 9. Consider the equilibrium between N2O4 dinitrogen tetroxide and nitrogen dioxide. Notice that they give us the delta H, that change in enthalpy for the reaction. It is positive. That means that this is endothermic. It means that we are adding this energy to the reaction. Since we're adding it, it's kind of like heat is a reactant. So it's kind of like heat is a reactant. I want to figure out what's going to shift equilibrium to the right. So what is going to cause equilibrium to shift to the right? Favor that forward reaction. So if I increase the temperature, that's like I have too much heat. Too much reactant is going to shift the reaction to the right so that I can get rid of that extra heat. So that one's a yes. How about pressure? Remember that pressure is all about moles of gas. Low pressure will favor more gas because those gases can spread out. High pressure is going to favor fewer moles of gas because they're all squished together and it's more stable to be fewer pieces instead of more pieces. So if I decrease the pressure, we're going to favor the side that has more moles of gas. On the reactant side, I have 1 mole of gas. On the product side, I have 2. So I'm going to favor the more. We're going to shift right since I have more moles of gas on the right than on the left. So yes. How about adding a catalyst? Will adding a catalyst shift equilibrium to the right? It will not. Remember that catalysts will speed up the forward and reverse reactions equally. And so we're not going to have a shift. We'll get to equilibrium more quickly, but we're not going to shift the position of the equilibrium. And so 3 is a no, 1 and 2 only is our answer. 2 more questions, and we're going to call this little piece of the answers done. Question number 10, which of the following is correct? These are all about weak acids. Remember that acids are always going to be proton donors. So I can get rid of my 2 answer choices that are talking about proton acceptors. Weak acids, in terms of conductivity, they are not good conductors. I'm going to get rid of my 2 choices that are good conductors. Final answer will be B. A weak acid is a proton donor, and it is a poor conductor. This good conductor that's a proton donor is a strong acid. Proton acceptor, good conductivity, is a strong base. Proton acceptor, poor conductivity, is a weak base. All right, last question, number 11. We have a titration to determine the concentration of an acid and found that the value has good precision but poor accuracy. Remember that precision is we have data that is repeated. So lots of the same values over and over and over. Accuracy means that we have the actual value, but we have poor accuracy. So we have gotten the wrong value over and over and over again. So consistently, which would give us that precision, doing the same thing over and over again, overshooting the volume is going to give us the wrong answer. This is our answer, but let's make sure that we have check the other answer choices just in case. Insufficient titration data isn't necessarily going to affect precision or accuracy, but it will minimize random error. We could have gotten lucky and had good precision and good accuracy, but we don't know. Choice C, how about reading the meniscus at a different angle every single time? That's going to also give us poor precision. So I shouldn't have repeated values over and over and over if I have a different angle every single time. And then if I forget to rinse one time, only one time, then I'm also going to mess up my precision. I will have poor accuracy and poor precision, and so we are confident that our answer is choice A.